Alright, buenos dias, clase. ¿Cómo estás? Muy bien, gracias. E2. That was how Dr. Adele always greeted us for an entire year in my high school, and so I thought I would share that with you. Alright, we got a couple things to cover before we get started. So I have put the test grades in, and you should be able to see those. And they were not super great. The average was much lower than normal, so on and so forth. And I am not super excited about how I wrote some of those questions. In particular, number 6 not only is written confusingly, I like 2/3 of y'all missed it. Maybe 8 of y'all missed it, like entirely. And so that to me means something is either I didn't teach it very well or whatever. So go back and look at how to figure out partial pressure. That seems to be a confusing topic. Go back, read it, and I'm going to let you guys have 2/3 of those points. I also originally, it was a larger question, and so I had more points allocated to it. I think I had a full 12 points allocated to it, which really the question does not warrant that entirely, I don't think. So all I have to say, we're not doing anything other than just allowing you to get 2/3 of the points back on that question, and then the normal quarter, points back for the other corrections. Okay, so just and hold me to that in case I forget that by the time I get your corrections. So let's just say also we'll say corrections due, let's say the 28th, and so just have those submitted by, let's see, Monday's the 1st. Let's say have them submitted by 4/2 at 8 a.m. Okay, so basically before our next class. Okay, that gives you plenty of time to do them. There's no reason you should be able to do it. The test was not super long or complicated, so take the half an hour, do them right, tell me why you missed it, and all that stuff, and you can have those points back there plus your quarter of the points back on the other ones. Also, a correction I need to make is that somebody pointed this out to me in an email, and I responded, and I don't think I've gotten a response back. The standard temperature of pressure is 0 degrees C, or 273.15 K, and 100 kPa. I don't know why I got it in my head. That standard pressure is 1 atmosphere, which is 101.325 kPa. So I am very sorry about that. I must have read that 12 times in making this test and just teaching y'all, and it never, somehow I just didn't make the connection that these were not the same thing, or I don't know what happened. Anyway, so sorry about that. This is correct. I mean, this is also correct, but that's not standard temperature and pressure. Standard temperature and pressure is this and that, which I think ends up being this. Okay, so just so y'all know, on this test, since I told you one thing, this, and the actual answer is that, either one of those was correct, and I didn't count off either on that question or on a question that you used either one of those values to solve it. Okay, so sorry about that. I don't know what happened there, why I didn't catch that earlier, but thanks to y'all that pointed it out. And if I'm ever telling you something different in the book than what is in the book, y'all let me know. Chances are it's just an oversight on my part. But if it happens that the book is wrong, we need to know that too, so I can holler at that guy and tell him that he's got some errors in the book. Okay, good. Sorry about all that. Test corrections by next class, 4/2, April 2 there. Let's talk briefly about homework so we can get some of those concepts pretty clear now that y'all have really had a chance to engage with that. Homework. Okay. You just guys had 4, 5, 6, and 7, and as we discussed last time, we've got a lot of this first part. We've got a lot of concept stuff, and we don't have a lot of math to be worked out. Okay. All right. So for heat of solution, just find that in your thing. Explain the concept of entropy. Okay, and I just want to go back over this because there's a little bit of back and forth on the group me. So we have entropy, which just equals disorder. Okay, that's really all it is, and so that's a statement. And then a second statement is that entropy is always increasing overall in the universe. Okay, so we had a little discussion about this last time, but there was some follow-up discussion in the Forster household, and so I wanted to sort of maybe clarify some of this stuff. So let's say. And again, we need to remember that this is not just like a clean room versus a messy room. Okay, so we have sort of we could say a macroscopic. Okay, and what does that mean? Macro is big, so we'll say a big scale entropy. Okay, and so what would that be? That would be like a messy room. Okay, and then we have microscopic entropy. Okay, and something that would be increasing in entropy. So a messy room, we would say, has more entropy than a clean room or an organized room. And so a similar situation, but on a microscopic level, a hot gas has more entropy than a cold gas. More disorder. Now, why would that be? Right? So you might say, that hot gas can do more work, or it can, keep somebody warm, which seems like a good thing, but it's not necessarily about a good or bad thing. And it's kind of a misconception I had for years and years. It didn't seem like entropy should ever be helpful because it's disorder. But entropy can be helpful. If you're in Antarctica, you will be wishing that a lot of the gas around you or your ice you're sitting on had a lot more entropy, because that would mean it's a lot warmer. Okay, so we're not asking you to identify situations where, we're not asking you to know hot gas has more entropy than cold gas. Although, if you think about it, it makes sense because each of those little molecules in the hot gas is really booking it. So they've got a lot of velocity and a lot of disorder. Whereas this cold gas, the colder it is, the closer they are to this state, where they all settle into nice little neat rows. Okay? And yeah, so they might be vibrating a little bit. Okay? And those are vibration marks. They might be vibrating a little, but they're a lot more ordered than like these guys, which are zipping all over the place. They're going crazy, okay? So a hot gas has more entropy than a cold gas, all right? And again, sometimes this can be kind of hard to figure out. The macroscopic stuff's not hard to figure out, right? Like a mug versus a broken mug. It's a terrible broken mug. Okay, so that's got, which one's got these more entropy? This guy's got more entropy, more disorder. Okay, now let's think about this. If we did work, let's say we had a little microscopic tweezer, whatever, and we were able to organize all these guys into this form, okay? Well, essentially, we would be doing microscopic Lego work, right? So like we had a bunch of Legos scattered everywhere. We put them all into a nice built square or cube, okay? So if building the Legos decreased their entropy, we'll say it decreased their entropy, so it increased their order by, we'll call them 10 entropy units, because the units don't matter here. This is the concept here, okay? Then, who's the most likely to play with Legos? Probably Andrew. Let's go with Andrew. So then if Andrew built this, okay, that means Andrew's entropy, which is a sum of all of the chemical and mechanical and kinetic energy that he has in his body, goes up. Andrew does this, so he increases Andrew's entropy by greater than 10 units, whatever it is, okay? In a perfect world, his would increase by 10 units, okay? But we don't live in a perfect world, and so there's always some extra that gets created, some extra disorder that gets created. And so some people talk about it this way, is that they call it the arrow of time. Which stretches from the past to the future, is actually, we perceive that. Now, that's a whole philosophy discussion, right? So bring that up in rhetoric. Y'all talk about it. All right? But does time exist? Do we just perceive it? Whatever. We're going to say time exists and we perceive it. All right? And the way some people talk about it is that the arrow of time is really just us being fooled by less entropy moving towards more entropy. Okay, so those are the same thing. And yeah. So anyway, all that to say that there's no way around this. You cannot travel into the past, no matter how many movies you see about it. You cannot fix it so that there's less entropy. You can't do it because of the laws of thermodynamics, okay? Which are not man-made laws, that they're laws that no one has ever been able to decrease. And I think there's some pretty strong theoretical basis for why you can't do it, okay? So anyway, explain the concept of entropy. All I have to say, it's disorder, okay? And we can talk about it as in terms of a mug breaking, a room going from clean to messy as you use it, okay? And like, this makes sense, right? Because what if you just were sitting in your room and it sort of, as you were living your life, your room got cleaner and cleaner by itself, right? What if, as you cooked a meal or cookies or whatever, your kitchen got cleaner and cleaner, your dishes got more and more orderly? You tossed a whole bucket full of marbles on the ground, and they went from a jumble in that bucket to a perfect cube on the ground, you'd be like, whoa, something crazy is going on here. Okay? It'd be like in the movie Interstellar or something. Just crazy, weird stuff that you can't explain. Okay? That's because those are all running in the wrong direction, right? Those are things never spontaneously go from from less orderly to more orderly overall. Okay? They do sometimes within a very limited area, but outside of that area, you end up with more entropy overall. Okay, and so we're not going to harp on that too much more, but I find it to be a really interesting topic, and so sorry. All right, so look at number 6 there on 286. Consider the 4 processes described in the accompanying table. So we have energy and entropy, increasing and decreasing in various combinations. Okay, and I want to talk a little bit about this because this is an ACT type question here. Okay, so we want to be able to break it down into what's different about these versus and then be able to categorize them. Okay, so we have entropy increases and decreases, increases and entropy increases, energy increases but entropy decreases, then energy decreases, entropy increases, and then they both decrease. Both increase, one increases and one decreases, and both decrease. Okay, so which way does we'll say nature, which way does the universe want things to run? It wants entropy to increase. Okay, that's what we just got done saying. Okay, and then if we flip back here and look in our chapter that you guys were referencing to answer these questions, we see natural processes proceed in the direction that reduces the Gibbs free energy in the system. Okay, so what does that mean? It means we want to decrease energy and we want to increase entropy. Okay, so number 3 is always going to happen because it's got both of those. Okay, but the flip of that is if we do the opposite, so we increase the free energy, and that it's not clear exactly what kind of energy he's talking about here, so we're just going to go with the Gibbs free energy because that's what is mentioned in our chapter. Okay, but if we flip it and we say we're going to increase the energy but then decrease the entropy, that will never happen. Okay, that will never happen. Now, these are decided whether they happen basically by temperature is what he tells us. Okay, so the S is our entropy term, I believe, right? I think I'm right about that. Man, where does he give us that symbol? Okay, well, I thought I saw it somewhere in here. Anyway, so temperature basically, if this whole thing goes negative, and if G comes out to be negative, then it happens on its own. Okay? And if it is positive, it doesn't happen. Okay? And you would have to force it to happen somehow, maybe by heating it to change this to make the whole thing negative. Okay? And again, we're not gonna focus a whole lot on that. It's a confusing topic that we really are not doing a theoretical basis for. So we're just going to leave it at that. We want to decrease the free energy and we want to increase the energy. Did I say energy? That's who's supplying your power. Entropy. Okay? All right. And then 7 is an electrolyte. What is an electrolyte? Where do we find that? Oh, in the section called electrolytes. Compounds that ionize in aqueous solutions. And he says that earlier. Okay. And basically, strong and weak. Strong completely disassociates, all of them. If you put 100 molecules in there, 100 of them disassociate. And weak ones are any ones that only part of them dissolve. Okay, where did he have that? Let's see where he. Here we go. Disassociates so thoroughly, they ionize readily, and the weak ones do not. And I didn't think he put a number on it, did he? No. There is a number in there that's about their solubility constant that like divides it. Kind of like we talked about with the ionic and the covalent. They just sort of arbitrarily gave it that thing that makes it polar or nonpolar and the thing that makes it ionic versus covalent. They just kind of gave us a difference in electronegativities and said, that it is what it is. And we feel like that was a good place to break it. So, all right, that's your homework. I hope that explains it. Kind of not super mathy, not a lot of problems to solve there, but good nonetheless because they're important concepts. All right, so I'm hoping you guys are marking up your chapter like I am trying to do here because we got more vocab, and this is going to help you in the future when we got a quiz or a test. It's going to help figure out what we got to do. I'm going to move this guy over here so we can focus on here. All right, ionic solids and water. Let's dig in. So first of all, solubility. We're concerned with how soluble, how readily things dissolve in some solvent. Okay, and it's good not to necessarily think about water all the time, even though it's super useful and super common, because lots of times you're dealing with stuff that where the solvent or the solute, neither one is water. Okay, all right. If you have dissolved as much as you can in something, it is saturated. Okay? And so the way you'll see that is and I like to use tea as the example, even though it is water. And I just said we don't always want to think of that. All right, so you have a certain temperature tea. You have a certain amount of sugar you want to dissolve in there. So you start pouring it in, and you start mixing it with your spoon. Okay. Eventually, you're going to continue to add sugar, and it's not going to dissolve anymore. Okay. No matter what you do, how hard you stir it, you can't make it dissolve anymore. And now sugar happens to be extremely soluble, and we're going to talk a little bit more about why that is here shortly. But it's extremely soluble. Salt is extremely soluble. And a lot of things are quite soluble in that you can put a lot of them in there. And at some point, it can even be where they'll dissolve so much, you're not even sure which one is the solute and which one's the solvent anymore. All right, so for many solutions, saturation point depends on temperature. So we've got a relationship that we want to talk about between temperature and solubility, and we're going to pick that up in a little bit later part of 10.2 as we're about to wrap up. Okay. Let's look right here. Just about any ionic solid dissolves in water to at least a minute degree. Okay. A working definition of solubility, we can say that at least 0.05 moles of a substance dissolves in 1 liter, then it's soluble. Okay? All right, so we just need to be clear about that. That's something, clearly I've boxed it, I've underlined it. Okay, so you need to do the same. What means something soluble? We can dissolve 0.05 moles. And note here, this is going to be important on the next lecture and then the rest of the chapter. We're always going to work in moles. We're going to work in moles of the solute in typically liters either of solvent, water, or of a solution. And we'll talk about the difference in those next time. Okay. And it's just a definitional thing, and you need to be careful as you're working some problems, but it's not super complicated. It's just two different ways to measure it. So anyway, he says not a good way to predict it, but we got some rules of thumb here. Okay. So note right here, guidelines are listed in table 10.2, which is right here. Okay. Important to note that all ionic solids with an alkali metal or ammonium ion as the cation are soluble. This is because they're always listed as exceptions to the rules denoting insoluble compounds. Now, if I was a terrible taskmaster chemistry teacher, I would make you memorize vast lists of soluble and insoluble compounds. And if you choose to pursue a degree in chemistry, when you get to, you might not even cover it in your Chemistry 101 class, your first chemistry you take in college, or even 102, but you will hit it in organic at very least, and probably inorganic as well, or I can't remember which one I just said. Inorganic and organic, you'll hit them. Because it's important to know that if I mix two things together and a various compounds, whichever compound, let's see. So if it forms silver iodide, I need to know like right offhand that that's going to be insoluble. Okay, and we'll see why. All right, so just generally speaking, we may have this may show up on a test or a quiz, and if you aren't familiar with it, it can be a little bit overwhelming because they all kind of look the same, and it's hard to tell which ones are soluble and insoluble, and then we got exceptions. What's the deal? All right, so let's go through it really briefly here. And I think a good way to do that is just look at this example here. Classify each of these compounds as soluble or insoluble in water, barium sulfate, and sodium carbonate. So let's look. Okay, barium sulfate. So we would look for right here, and we would say, oh, good, it's soluble. Uh-oh. But there's a significant exception that means that these exceptions are not soluble. So we would say that it is insoluble. Generally soluble, sulfates of barium are listed as an exception, thus it's insoluble. Okay. Carbonates are generally insoluble. What's that? Boom. Here we go. Carbonates. Okay, so we're kind of back to these polyatomic ion names that we thought we had left years behind, right? However, all ionic compounds with an alkali metal as the cation are soluble. And so, is that an alkali metal? Barium. What do we have? We have the alkyl. What are we saying? Alkali metals. I guess they're saying either one of these, because you have the alkali and alkali earth. Anyway, all right. So you see how to use it though. Carbonate, and then you look and see if there's an exception. If yes, it's the opposite. You're in the insoluble, so it's soluble. If no, it goes with whatever the table's for. Okay. All right. So pretty straightforward. We're not going to do a whole lot of that. I would expect to see maybe one or two of those on a quiz, kind of like he's got right here, just so you guys are familiar with how these tables are typically set up. All right. He's a lot more amazed by salt not dissolving in oil than I am. But anyway, so he says ionic solvents typically don't dissolve in nonpolars. All right, so we're going to hit polar molecules first. All right. All right, so like dissolves like. Okay, so what are we talking about here? Okay, I'm talking about the thing you can't see. There we go. All right, so like dissolves like. What does that mean? It means polar molecules dissolve polar molecules, and nonpolar dissolve nonpolar. Okay, and it's got to do with the intermolecular forces, okay, that we've talked about. But this is this is good. Polar solutes dissolve in polar solvents. Nonpolar solutes dissolve in nonpolar solvents. And not the other way around. They don't dissolve in the opposite one. Okay? So we've got some polar molecules here. They're showing the actual structure of them to kind of show you why they're polar. And this is just a good little intro here, just in case you ever are curious. It'll give you a good basis to look up, or when you hear it again in chemistry class. Substance called alcohols. Okay. It's because they've got a hydroxyl group, which is the OH there. And you can see that when you write it, you don't just say CH4O. You say CH3OH, because it's kind of showing you, like, what is this? CH3, 1, 2, 3, OH. Okay, and we could do the VSEPR stuff, right, to figure out, oh, there must be some electrons up here to give it what? That bent shape, remember? So this would be a trigonal planar as far as the overall structure is, but then it would be a bent molecular shape, right? All right, but what is that? It means that not only do we have this O on the OH, this oxygen hanging out, which is very electronegative, we've also got clearly some free unpaired electrons here, which of course makes this very polar, which lets it interact with water. Same thing here, CH3, CH2, OH, CH3, CH2, OH. Okay, and so these are, you can see that these sort of have this same structure. You got a CH3, then you got a CH something attached to the OH. Okay, just one of them, CH3, OH. There's no second C there. This one's got 3. Okay, CH3, and there's 2 of them, so it's CH3, CH3, CHOH. Okay, so that repeating pattern with that OH hanging on there is what makes those things an alcohol. Okay, and so it just, again, it's interesting to sort of think about, like, we just think of alcohol as, like, you know, the kind you drink, which is ethanol up here at the top, that first one. Okay, and you make one little change. It's got a lot of the same properties, except if you drink it, it causes you to go blind, crazy, and if you drink enough, death. Okay, so that's methanol. And then isopropyl alcohol. This has got to do with the structure, just, again, for your benefit, I guess. We won't be testing on this, but their shapes matter, and you can actually have the same molecular formula and have a different shape, and it actually has a different name. And they add 1s and 2s and stuff in here based on where things are bonded in the molecules. So anyway, all I have to say, these are totally, have we used the word miscible yet? Did we use that the other day? I think we did. Yeah, I thought, well, if we hadn't, I thought we I thought we used the word miscible, but and maybe we did. I just can't find it right this second. But so miscible means just totally 100%. You can mix as much of them together as you want to. And alcohol and water is that. So you can have something that's 100% alcohol with very little water in it. Have something that's 50-50 or mostly water and just a little bit of alcohol. It's not gonna matter. They're completely mixed and they'll never unmix on their own unless you go to the trouble to boil them or whatever. All right, so we just do need to know a couple of things that twice as volatile as water, which just means what? The tendency to evaporate, right? We talked about that in the last chapter. It was on your last quiz. They're also famous for being flammable. And anybody who has ever seen a movie with any kind of thing like that knows that alcohol burns. You can buy alcohol candles. All right, and that's related to them sort of being volatile. They oxidize pretty regularly, pretty easily. All right, they don't have a charge though, so they're not ions. All right, let's just keep that in mind as we go through. All right, nonpolar liquids. Okay, so while these have that polar section that's going to be pretty electronegative, we don't have that in things like oils and greases. Let's see. Yeah. And I think probably the takeaway from here is basically this. Molecules of greases and oils are all nonpolar. Okay? And so they can dissolve other nonpolar things. He says nonpolar solvents, if you guys have ever painted with oil paint and then try to get it off your hands, you've got to use mineral spirits. And these are other, if you've ever smelled them, you'd never forget it again. But so these are nonpolar solvents. There might be a question something like name 2 nonpolar solvents, okay? And I'd stick with gasoline and mineral spirits. Just they're the easiest to memorize, okay, or remember. All right, so they only have a very, let's see, main forces holding the molecules together are London dispersion forces, which tends to make them pretty easy to vaporize because they are not held together by those hydrogen bonds, and so they can just kind of do what they want and evaporate at pretty low temperatures. Okay. We're going to fly through this section right here, solutions of solids. I think it's kind of an odd way to say it, but it is what they are. All right, so while they're liquid, you can mix these various things together, and then as they quote unquote freeze or become solid, you can they stay that mixture. The mixture doesn't go away just because they're now a solid. Okay, so what do we call that in metals? We call that metal alloys. All right, solutions of solids. So this is a good thing. Just some more vocab here. Carbon steel, less 2.1% or less carbon by weight. All right. And note that that's by weight and that's not a molar deal. So if I put 100 pounds of iron in there, and then I add 2 pounds of carbon, even though those molar ratios are going to be way out, that's still not considered carbon steel, or that's still considered carbon steel because it's less than 2% by weight. Okay, so you can see this carbon atom is much smaller than the iron atom that surrounds it, but it does things to make those molecules act very differently. Okay, if carbon is greater than 2.1, the alloy is known as cast iron. It's extremely strong, but also very inflexible. Okay, the brittle is the word we want to be familiar with still. if you have ever done plumbing work, you may have run across a cast iron fixture. And so what would happen, like if you hit a spoon in your drawer, like you got out an eating spoon and you hit it with a hammer, it'd probably bend, right? You hit it with a hammer, it's going to deform, it's going to have a big ding in it, or maybe be flattened a little bit. But it's not going to shatter. Well, cast iron, because it's so brittle, you actually can't do anything with it. You hit it with a hammer, it will split right down the middle immediately without a second thought about it. So if a cast iron fixture is ever stuck on something, you can't get it off, hit it with a hammer. That sucker will come right apart. Okay, that's because it's so brittle. So you have to heat it into liquid and then pour it, and then it's fixed. So that's more than 2.1 percent by weight. Okay, stainless steel, you just need to know that it has chromium and nickel in it that move around and get to the surface and protect that iron from oxidizing to form rust. Okay, so it actually forms what's called a protective oxidation coat. So it does oxidize, but then it stays there and protects the rest of it. I'm not super interested in going into a big discussion about gold and silver. I do think it's good to know that brass is an alloy of copper and zinc. Just know that. Does it have bronze in here? The reference it right here. Okay. Maybe it's on the next page here. Yeah. Bronze is a copper alloy, usually containing tin. Okay. Anyway, just some nifty information there you can read about and learn about that. I'm not going to spend any more time on that, though. All right, really quickly, I want to talk about how they make soap, because first of all, it's super interesting, and secondly, it's actually applied stuff. Okay, so that's always nice to get that when we can. All right, so legend has it that soap was discovered when rain running from animal sacrifices made at a temple on Mount Sapo flowed into the Tiber River near Rome. Okay, a crude soap had been formed, and the women saw that it washed clothes more effectively. Can you imagine trying to wash clothes without soap? Like, of course, everybody's clothes were super dirty. They didn't have soap. Of course, they were super dirty. They didn't have soap. That seems crazy to me. Soap is so basic. But fats from the burnt offering, wood ash from the fire, and the heat of the fire. So basically, the fat dripped down into the ashes where they mixed, and the rain washed it all away. And so saponification is what that's called. They have both of their roots in Mount Sapo there, as far as their etymology of those words. And what you end up having is you can read about all the different types here and the glycerol and all this stuff. But here's the key. I thought this was a good explanation. Okay, so we saw this red one, the alkali metal ion, and he talks about that in this paragraph here. Boom, that pops off, and now this is able to make this whole molecule dissolve in water. Well, sort of. It sort of keeps it attached to the water, but the long tail of it over here. All right, so where do we say? The glyceride ionized to form the stearate ion. Don't worry about all the things. Just know that that end little thing popped off. The oxygen that was where the K or N was attached is now an O negative ion and is attracted to the partial plus regions of the water molecules. Okay, so that means it dissolves. That's what being attracted to polar molecules means. It dissolves in those polar molecules. But the long carbon chains of these anions, being nonpolar, okay, so there's nothing polar here. They're all evenly, the charges are all evenly spread around, are jostled around because the other water molecules don't want them there because they're all hydrogen bonded together,
Whereas this guy is not hydrogen bonding with any of them, so he's just kind of being squeezed in and out, and squeezed in and out, and moving around. And so what does it say? So that stearate carbon chain, that long carbon chain, is looking for a safe place to get out of the way of the water. So that's what makes it hydrophobic, hates water. And what does it do? In the presence of particles of nonpolar oil or grease, what happens? All those soap molecules, boom, turn their long stearate tails into that grease, and they dissolve there. So the nonpolar part's here in the middle, and the polar part's out here, and then it's all linked together. Just because one part dissolves and another one doesn't, these are still linked. They're still bonded right here. Okay, so they end up forming this. All right, and if y'all remember, you might remember from biology last year these words. Phospholipid bilayer. Okay, that is what makes up a cell wall. Okay, now it's not soap molecules, but it is long chains of carbon with a hydrophilic head, or a head that is able to be attracted to and bond with water in hydrogen bonding. Okay, so you'll see it kind of looks like a cell wall, like maybe from an early type of cell. It's the same process, slightly different molecules, but the same process. Okay, so anyway, you just need to know they have a hydrophilic head with a hydrophobic tail, and then they can attach to both grease and water, and then get washed away. All right, cool. Gases in liquid solutions. Okay. Unlike other solutions we've discussed, the solubility of gases and liquids is strongly affected by pressure. Okay, so solubility of gases and liquids strongly affected by pressure. So you can see what's going on here. We've got these gases up here, and then we've got the liquid vapor molecules. Okay. And they're moving around in this headspace up here, and some of these gas guys are going down into here. An equilibrium exists. Now that equilibrium doesn't mean nothing's happening. It just means it's staying in the same place it basically was, right? So you have some that are going into solution and some that are coming out of solution, going into the liquid and leaving the liquid at the same rate. Increasing the gas pressure results in the gas dissolving at a faster rate. So when I make beer, you have to carbonate it. So you have to push CO2 into the uncarbonated beer at a much higher pressure than you actually get it out of the container. So I basically turn it to 30 psi, and that pushes the CO2 into the beer pretty quickly. And then, but when it's been carbonated after about 24, 36 hours, you turn it down to 15 psi, and then you can distribute it using that pressure. Like you can put it in, it comes out of the keg and into a little glass or whatever you're drinking out of. But the higher the pressure, the faster the gas goes in there. So we need to, that would be a perfect little quiz question right there. So it's, let's see. Yeah, so when you open a container of your favorite soft drink, the pressure in the container drops to atmospheric pressure. So those cans are pressurized, right? That's why you can't squish them. They're not squishy. They're tight. They're hard. It's not because the aluminum can there's in is so strong. It's because it's under pressure, right? You can squish a can once you open it and release that pressure, all right? And so what it does is that brings it to atmospheric pressure, and it reduces the solubility by a factor of 5 to 10, which is why all they effervesce, another vocab word there, and fizz. Okay? And it becomes flat because that CO2 eventually comes out of solution. Okay,
should be pretty intuitive because y'all have all picked up a Coke that you thought was yours and turns out it was somebody else's and they left it open a day before and it's flat, which is no good. Okay, good. It also depends on temperature, and I don't think he even really talks about that. And, well, maybe he does here in temperature and solubility. All right. Now, this is where your homework is going to be related because it's important graph reading abilities as well as some pretty useful information, even beyond being able to read the graphs. All right. Temperature of a solution can have a pronounced effect on the solubility of both ionic solids and gases in aqueous solution. Graphs show solubility. We'll get into that in just a second here. The vertical axis indicates the percentage of total mass that's due to the mass of the solute. Okay, so that's kind of an interesting way to do it because it's not saying a certain amount of grams going into there. It's saying what percentage does it make up of the solution mass. Solubility of salt is almost flat. It does increase with temperature, but only increases about 2% over the temperature range of liquid water. Okay, so where is that? Let's find it. So here it is right here. And see it's one of the flattest ones. And then interesting, lithium sulfate actually decreases substantially, which is not normal. Okay, most of the trends, as you can see, are upward there, or at least flat. Let's see. 1014 is the solubility of common gases. Okay, he does talk about it. There we go. All right, so note that it's actually the opposite. Okay, and actually CO2, look how much higher it is than oxygen as far as solubility goes. CO2 is way up here, but look at all the trends, right? So temperature, as it gets hotter, solubility goes down. Hydrogen sulfide goes down, CO2 goes down, oxygen goes down. Okay, so I want to talk about two of these. This is interesting, Cl2 gas. The solubility of that matters because that is how we disinfect water, drinking water. And if it's too hot, it can make it to where you're not getting the dissolving that you need into a solution with free chlorine in the water to kill all the bad bacteria. Okay, so you do have to take temperature into effect as you are disinfecting. So the water coming out of the ground is typically the same-ish temperature. It's like 45 or 50 degrees, so it's pretty cold. But as it travels through pipes, it may warm up, and you can see it only has to go up 15 degrees for it to drop dramatically by half, 2.5 down to 1.25. Okay. So what does that mean? It means it's no longer soluble in there, and it comes out of solution. Okay. And we'll do a little more discovering of that with our homework. All right. But and the other one I want to talk to you about is I'm sorry, I'm making you guys seasick here. All right. Let's look at oxygen. And I hate that this is so low down here and you almost can't see it. But it is decreasing. Okay? And so when would dissolved oxygen in water be important? Well, it's important to fish. Okay? And so often where you have a large body of water, if it gets super hot, the dissolved oxygen can actually go down enough to where the fish don't have anything to breathe anymore. And that is a bad situation because they then die. You have a giant fish kill, which is
terribly, not to mention, terrible for fish, and not to mention horribly smelly as well. All right, good deal. So basically, we just want to look at and see that some of these go up drastically. They are, and all of them generally go up. And some of them start very low and get very high. So potassium nitrate's a really interesting one because of how much it changes. So anyway, we'll look at that. I'll get you guys a graph and some questions about it so that you guys can start working on some of those. It's kind of interesting and it's a useful thing to be able to do is read those graphs. I like that he says this. Solubility of oxygen is very low, but apparently it's high enough for the fish to be happy. Yes, apparently it is. Solubility is relatively constant. And does he even have? He has oxygen on the next page, but again, it's super low and kind of hard to see here. But do know that it does generally decrease for gases and increase for ionic solids there. Okay, good. That's going to cover 10.2 for us. Again, a lot of concepts, a lot of vocab, so just kind of be storing that stuff away. Not going to be long before we've got either a test or a quiz coming up. Let me see where we... Yeah, we got a lot going on in here still, I think. Probably got enough for a quiz and a test here. So just look for that. I think I've got all that stuff planned out in the I was going to say activity sheet, assignment sheet. But do your test corrections. I will get you guys homework out on, I don't know when it'll be. It may be as late as Sunday. I just we are tied up and I'm out of time on a bunch of things. Tomorrow I've got ACT and all that stuff that I'm doing tomorrow night, and so I don't know when I'm going to have time. But I'll get it to you, and I'll let you know when I get it to you. Any additional instructions, and so we'll be doing solubility, and we'll push on through 10.3, and then we will just keep trucking towards the end of the year. All right, guys. Sounds good, and we will talk soon. Thank you.